Hello dear students, welcome to this additional video lecture that should give you an introduction or a reacquaintance with matrix algebra, and it's going to be focused on how to implement it in Excel with examples for portfolio theory. So it will be very hands-on, so it's relevant for what you're currently doing. Here's the brief agenda. Today I'll start with a simple matrix algebra for 2 lines, something you really don't need matrix algebra, but it helps you understand what's going on or how it works. Second, I'm going to discuss some general properties of matrices and matrix operations, and I'm going to conclude with several examples of using matrix algebra in portfolio theory. So let's get started with a simple example. So typically we want to find a solution to a system of equations. So we have many equations, let's say 100, with 100 unknown variables, and we want to solve that. Very straightforward, perhaps, but kind of time consuming if you wouldn't have matrix algebra. So let's suppose we have 2 very simple lines. Y is 2 plus 3x, and the other one is y is minus 2 plus 4x. As long as the lines are not parallel, which they are not in this case, they must intersect at some point. And at that particular point, y and x will be the same for both lines. So let's see how we get there. So this is a visual presentation of the 2 lines. So the red one is the one that intersects the y-axis at minus 2. It has a steeper slope, and the blue one intersects at plus 2 and it has a somewhat less steep slope. And it's obvious that the intersection is at x is 4. How do we solve this with matrix algebra? Well, to get started, we rewrite the equations a little bit. So we started with y is a1 plus b2 times x, and a2 plus b2 times x. So this is to make it general, so we can substitute any number for a1, a2, b1, b2. But the whole idea is that these things get real numbers in there. We're going to rewrite that by moving the expression with x to the left-hand side. So both y and x are moved to the left-hand side. And so we get y is minus b1, x equals a1, and y is minus b2, x is a2. And that gives us essentially 2 equations that we can rewrite in the form of matrix algebra. And so we can do that, and you can see that in the bottom line. So I start with a matrix of minus b1, 1, minus b2, 1, as the square matrix essentially here. Then we get a column vector x, y equals a1, a2. So this thing at the bottom is the same thing as in the middle and at the top. It's just a rewriting. And then, you can read this one if you want. So a1 and a2, that's equal to minus b1 times x plus 1 times y equals a1, and that's essentially the first equation. So this is how to make a matrix from that. And then we could, take this thing with a symbol, and we call it simply fat letter b times d equals a. And we use the fat letter for square or bigger matrices, and the small letters for vectors. Right. Okay, and so B is a 2 by 2 matrix, D and A are column vectors. So how to solve for the intersection? Well, that's essentially quite simple. We have, of course, the 2 matrices here, B times D equals A. And so we need to solve x, y. And in a normal equation, if you have like, you know, A times x is B, we would simply move the A to the other side and we would divide by that. So what we would want to do is say D is A divided by B. But that's not how it works in matrix algebra. Then you don't use the division, but you use the inversion. And so that's how to do it. So D, the column vector with x and y in it, equals the inverse of matrix B times D. And so we need to calculate the inverse of matrix B. That's this one. I explain you later how to do it. And you multiply that with 2 minus 2. And if we do this exercise, then it gives us an answer of 4. That's the x coordinate. We already knew that or guessed it. And 40. How do we get it? Well, 4 is equal to 1 times 2 plus minus 1 times minus 2. So that's 4. And then the second element in the column answer is 4 times 2, which is 8 times minus 3 minus 2. That's plus 6. 8 plus 6 is 40. So this is how you will get the answer. Well, I've shown you how to do it with a small scale example. You may not immediately get it all from just watching this video. So I recommend that you simply try to reconstruct it and try to see whether you can trace back the numbers also with some of the stuff that comes later in this video. So try it at home with your Excel with the matrix functions that we are going to see later on, but just watching the video is probably not enough. You need to do this. Really, it's a very practical thing. So second part of this presentation is about the general properties of matrices and matrix operations. So of course, for simple problems, 2 equations with 2 unknown variables, you know, we kind of are able to do that. At least I hope so. So where it really comes in handy, if I have like 100 equations with 100 unknown variables or even worse. And this is typically what happens when we try to solve for optimal portfolios. So you could in principle do that with 10,000 of stocks. And so you don't want to do this all by writing it in, you know, the typical linear algebra way that you've been taught in high school. So, but before you can really use this toolkit, you need a little bit of background knowledge. And I'm giving you the bare minimum with a lot of explanations on the whys and hows. But first of all, you need to realize that the matrix has dimensions. This is of course not very new, but you know, so we have square matrices like the one here. That's a 2 by 2 matrix. So the first number indicates the number of rows. The second indicates the number of columns. So a 4 by 1 matrix has 4 rows and 1 column, and therefore it's called a column vector. Likewise, 2 by 4 matrix, 2 rows, 4 columns. 1 by 3, that's a row vector. 1 row, 3 columns. So you don't need to be Einstein to get this. Now I'm going to discuss a few functions or commands or operations, whatever you want to call it. And the first one is the transpose function. This is something you can do in numerous ways, but in the Excel framework you use the transpose matrix function. And that switches rows into columns. So suppose I have a column vector 1, 2, 3, and I really need a row vector because, as we later see, this may be important in certain operations. So then I first need to do a transpose. So W is the column vector, but if I use an apostrophe here, then it indicates that I transpose the column vector and it becomes a row vector. It's not restricted to vectors itself. We can also use matrices. So suppose I have this matrix with A with the first row 1, 2, 3 and the second row 4, 5, 6. if I take A apostrophe, do a transpose, so the first row vector becomes the first column vector, and the second row vector becomes the second column vector. Another thing that you need to know is that in matrix world, the number 1, of course, exists, but then as an element of a matrix. But if you want to talk about, the equivalent of the number 1 in matrix form, you would talk about the identity matrix. So what is that? It's a square matrix, and it has the number 1 on the diagonal, and all other elements are equal to 0. So the most important operation is, I would say, the matrix multiplication. And yeah, there's a lot to say about that, but essentially you can multiply two matrices with each other. And that's a very weird operation, because what you essentially do is that for the answer you will get a cross product. So let's have a closer look at that. So A times B equals C. So let's suppose that we're looking at the element on the second row in the third column. How did we calculate it? Well, that's the cross product of the second row of the first matrix and the third column of the second matrix. And so we get here the number x would be equal to 1 times A plus 2 times B plus 3 times C plus 4 times D. So, and we add it together. So it's a summation of cross products. And each element of this matrix C is calculated in this way. So a lot of calculations, but you could redo them manually, and I recommend that you do it just so you understand what this operation is doing. It looks very magic, but in a sense it's just a way of calculating a lot of cross products. So that's what it does. So each element ij of matrix C is the sum of multiplying each element of row I with column j. And to make this work, the number of columns in matrix A must be the same as the number of rows in matrix B. That's important, otherwise it won't work simply. And it means that the dimension of the output matrix C are equal to the number of rows of matrix A and the number of columns of matrix B. So the order in the multiplication is important. You cannot do B times A in this case because B has 5 columns and A has 3 rows. Yeah, well, having said all this about matrix multiplications, of course, they can be a bit annoying, in particular when you implement it in a spreadsheet. But they mainly simplify notations. And in the end, they also access a lot of powerful functions in Excel, or if you do this in MATLAB, Python, or whatever, it really makes your spreadsheets or program much easier to read and also easier to implement. However, you usually need to think more carefully about the implementation, and of course that has to do with the issue that I raised in the previous slide. So the dimensions need to match. So what kind of matrix functions are there in Excel? Well, we can multiply matrices with the Excel command matrix multiply, MMult. It has two inputs, range 1, range 2. Of course, we can transpose a matrix, transpose range 1, and we can invert a matrix, matrix inverse. In brackets you'll find the Dutch equivalents of these commands. So typically you would do this by first selecting the dimensions of the output matrix and then enter the command and press Shift Control Enter. But later versions of Excel are much more lenient in this, and I don't think you have to do all this. But I'll explain it as if you still have to think very careful about how to do it in Excel. So, how to use this in Excel? Suppose that you want to calculate a portfolio return using the matrix multiply function. So I have a row vector of portfolio weights, ranging from B2 to D2, that's 50%, 20%, 30%, and I have a column vectors of returns for each security, then I can simply use the matrix multiply function. So I would type in cell D6, I would type the equal sign, then press MMult, open bracket, select the range of the row from B2 to D2, then enter the second argument, the column from B5 to C5, and I would conclude that with Shift Control Enter. In modern versions of Excel, you can often just press Enter, and an Apple machine also works differently. This is exactly the reason why you need to be present in the practicals, because there we're going to work with the Office version of Excel. And that's also the version that you need in the exam hall for the Excel assignment. So make sure that you attend the computer practicals. So once again, you just cannot multiply any couple of matrices. The dimensions need to match. The number of columns from the first argument needs to match the number of rows from the second argument. Before typing the matrix function, figure out the size of the output matrix from the operation, because it's more difficult to change this afterwards. So another useful function is something that is known as a dot multiplication. So A times B equals C, where Cij is equal to Ij times Bij. So essentially, element by element, you multiply the elements of the matrix. And so for this, of course, the dimensions of A, B, and C need to be the same, otherwise it simply doesn't work. And so this is known as a dot multiplication. We're going to need this one too. So here's the transpose function. I talked about that before. So suppose that, I have already the same spreadsheet as before. The weights as a row, but for one reason or another, I want to have them as a column vector next to the returns. And to do that, I would select the area C5 to C7, and then type equal, and then type transpose, open bracket, B2, D2, close bracket, Shift Control Enter. I think we captured all the basics, except for the matrix inverse, but we'll deal with that later. So let's try to apply this in portfolio theory. So when you want to calculate the standard deviations of the returns of a portfolio of two stocks, you would simply use this equation. The standard deviation of the portfolio is equal to the square root of the portfolio weight of security 1 squared times its variance, plus portfolio weight 2 squared times its variance, plus 2 times weight 1 times weight 2 times covariance between 1 and 2. Quite an okay formula. So in matrix notation, we would write this as the square root of W apostrophe, meaning I transpose a column vector, so I have a row vector of security weights, times the big sigma, which I use as the symbol for the covariance matrix, times a column vector of portfolio weights. So also a simple formula. But now you will see that with 3 securities, my normal linear algebra notation becomes already a bit tedious. So I have 3 times this weight squared times variance thing going on, and you have 3 times a covariance term. And yeah, that already becomes a bit more tedious. And this is for 5 stocks, so that's already pretty horrible. But in matrix notation, that's still the same. So you can see that this way of writing down formulas is really helpful in cases of a lot of stocks or a lot of equations. How to do this in Excel? Well, Suppose I already have portfolio weights here. I have a example with 5 stocks, A, B, C, D, and E, all in column A, and in column B I have 5 portfolio weights, 10% for A, 30% for B, 5 for C, 20 for D, 35 for E. And I have a covariance matrix. You know, for the moment, just assume that you already calculated in some way or another. And so, how to do the calculation now? Well, I can start essentially with in a two-step approach. The reason is, why do I do it in 2 steps? Well, the Excel matrix multiplication function only takes 2 arguments at the same time. And now I really need, you know, 3 arguments, because it's the row vector of portfolio weights times the covariance matrix times the column vector. So in step 1, I just multiply the covariance matrix with the column vector. And that one also has as an output a column vector. I leave it to you to figure out why that is. But so if I multiply the area from B2 to B6 with the covariance matrix, so I will get essentially the output that's written down in cells E9 to E13. So 0.02694, 0.03915, etc., etc. And then in step 2, I calculate the matrix multiplication of the row vector of portfolio weights with the column vector of step 1, and I take the square root out of that, and that gives me 21.2%. So yeah, I invite you to do this at home. I will also give you the Excel spreadsheet so you can figure it out yourself. And we're going to practice with this also during the computer practical. So let's go to a more serious setting now. We want to calculate our first portfolio. And this is a bit of a preview on next week's class, but you know, just as an introduction, it won't hurt you. You can read it also in Francis and Kim on page 154 if you want to have more explanation. We're going to calculate the minimum variance portfolio, and this is really a very interesting portfolio because in practice it really performs well, so it's not even a bad portfolio. And what is it? It's of course the portfolio with the lowest risk possible. And the formula for that is the one that I present here. So the column vector of minimum for variance portfolio weights is equal to the inverse of the covariance matrix multiplied with a factor of 1s. And this factor of 1s is usually identified with the Greek character iota. And so that's it, and that creates us a number. So that's the top end of the division symbol here, and that's divided by the same thing but then multiplied with a row vector, and essentially that is scaling the number into one that adds neatly up to 100%, and we want of course portfolios that add up to 100%. So even though this is an how to do it video, you can see that the minimum variance point is at the end of the arrow here. So that one is pointing to the minimum variance portfolio. And so that's what we are looking for. And so how to do it? Well, the formula involves the inverse of the covariance matrix. And the Excel function for that is M inverse and then the range. So one particular thing about the inversion of a matrix, it can only be done on square matrices. So 3 by 3 matrix, 4 by 4, 5 by 5. And also the destination is also 5 by 5. So it's good practice to first select the destination range, in this case a 5 by 5 matrix, and then type equal M inverse, open a bracket and select the input range, enter a closing bracket and then press Shift Control plus Enter. As I told you before, probably your version of Excel does no longer require to use Shift Control Enter, but in any case, this is the safest way to do this. So here is the covariance matrix, and the inverse of the covariance matrix is here. Sorry, I was wrong about it. We're looking here at the inverse of the covariance matrix. That is usually a very difficult matrix to read because the numbers don't have any practical meaning as far as I know. But if you want to check whether this is really the inverse of the covariance matrix, you could multiply it again with the covariance matrix in the inverse of the covariance matrix multiplied with the covariance matrix itself should give us the unity matrix. So a matrix with ones on the diagonal axis. So once again, the inverse of the covariance matrix in the blue circle, which is the outcome of the M inverse T2H6 part, where the covariance matrix is. And there's a column vector of 1s in column J. And then I do it again in 2 steps. Matrix multiply the inverse covariance matrix, so D18 to H22, multiply that with the 1s, gives me what is here labeled as the denominator, and the denominator is actually the sum of all this, and this is actually the scaling part. And if I divide each element here by the 44.76, I get the optimal portfolios here, and they're kind of hidden behind this insert of my video, but you'll see it in the Excel sheet. That's a neat vector adding up to 100